So, hi, I'm Aäron Munsters, a PhD student at the Vrije Universiteit Brussel, and today I'm presenting to you JASMaint, which is about providing a portable multi-language taint analysis for the web. And this work has been performed by Abel Stuker who, in the context of his third bachelor thesis. So before I get started, I would like to introduce to you an example of a JavaScript program. So here you can see a JavaScript function replace, which has the goal of to, given a text, replace a certain pattern by a certain replacement, and then return the replaced text in which each occurrence of that pattern has been replaced. You could use that replace function, for example, to replace the template recipient with a runtime value, the recipient's name. And you could also to replace it in an email, or you could also, for example, replace the template timestamp to replace the current time in a certain log statement. Now, given that this is a WebAssembly session, you can also use that function replace as an import from a WebAssembly file. So someone has then developed that replace function in WebAssembly, compile it in a higher level language, C, C++, or Rust, compile it to WebAssembly, and then you can still reuse that same functionality. But let's imagine that that replace function is a little buggy. Sometimes it might reuse arguments from the previous call in the next call. So it could be that that recipient's name might end up in the log statement. And that recipient's name might be in control of some user who is a little hacky and try to inject an SQL statement to essentially drop the table employees. And eventually that log statement might end up in some database and you lost all your data. Well, it's quite crucial to sometimes understand the WebAssembly programs, their behavior, and it's not always easily to do so. WebAssembly programs, they typically are included as they come from third-party vendors. They might be fetched over an insecure network, and within a single program, you might mix and match secure and insecure input and give it to a WebAssembly, one of those WebAssembly instances. Now, if you check the news lately, you can see that actually NPM has been an attack surface for supply chain attacks, and that both JavaScript and WebAssembly programs, where they interoperate, have been actually the target for such attacks. Now, in a more broad sense, we would like to, for interoperating programs between JavaScript and WebAssembly, researchers and developers might want to better understand the runtime behavior and the data flows of the programs under varying conditions for detecting undesired, unsafe, or malicious behavior, to perhaps analyze malware or to debug applications. And one way to do so is through a dynamic taint analysis, which is to monitor data flows through a program at runtime by labeling data with taint. And so there's three key phases. First of which is to mark taint sources in your program, there where values originate. And so throughout this presentation, I will use U to denote an untainted value, considered secure or irrelevant. And then T for tainted values, which is critical information that enters a program. Then in the second phase, the program is executing, and through taint propagation rules, the taint will be kept track of throughout your entire program. And eventually there you can mark sinks in your program through which you want tainted values not to flow. Otherwise your tainted analysis should report that something's wrong, that a tainted value reached a sink. And to couple back to the earlier example, you could, for example, mark the recipient's name to be a tainted value, and you could say that before you write something into the database store, you could mark the value that is being passed to the store as a sink, or that it's now about to reach a sink. So ideally, this program would panic from the taint analysis point of view. In the context of taint analysis, you define your taint propagation rules, and either they are available and correct, for which you can then consider your taint analysis to be precise, but if they are missing or incorrect, the analysis is imprecise. And then you have two cases, one of which is that you overtaint values, that is, you mark a value of tainted, whereas in reality it should have been untainted, for example, passing a safe string to the database, but the analysis panics. Or you have under-tainting, in which you have a value that is marked as untainted, but in reality it should have been marked tainted. You pass some dangerous string to the database, but the analysis does not notice. And so we state that there's a lack of taint analysis precision for multi-language applications. That is, with current state-of-the-art dynamically analyzing JavaScript and WebAssembly interoperating programs, the analysis will either under-taint or over-taint, as you have no way of tracking taint for such interoperating programs. So we developed JASMaint, which is a multi-language taint analysis. And we wanted it to be portable, but before we built JASMaint, we first individually developed a dynamic taint analysis for JavaScript, another dynamic taint analysis for WebAssembly, and then we provided an orchestrator to essentially combine the two taint analysis to reason about multi-language applications. And one also key aspect of our implementation is that we wanted it to be portable. So essentially to have that analysis be deployed in multiple contexts wherever that JavaScript and WebAssembly programs can interoperate. So what I will show next applies to both the JavaScript and WebAssembly taint analysis. In terms of their portability, how we achieve portability is through using source code transformation. So for both languages, we will use an instrumentation platform that takes in any target program that we provide essentially an analysis, and then that instrumentation platform will rewrite the target program, inject the analysis, provide you a new target program that you can then execute, and then from that running process, understand its behavior. So in this context, the target program will be rewritten to inject taint tracking analysis, and then the idea is that that program can be deployed in these different contexts, server-side, client-side, or in the cloud. Great. So regarding the roadmap, let's dive into the details of the JavaScript taint analysis. So to develop the taint analysis for JavaScript, we use the frameworks Aäron and Linvale as a source code instrumentation platform. And we essentially use a shadow values to track taint. So for example, on the right-hand side, you can see an uninstrumented program which would have the value foo. Well, the shadow value representation of the value foo would be essentially an object that has an inner field, which is still that value, but that object is then, with our taint analysis implementation, also augmented with a _ taint field, in which we essentially can keep track of the taint of that value. And besides the using shadow values, we also had to account for taint propagation. And so we provided taint propagation rules for intrinsic functions, which are functions provided by the VM, such as, for example, the join function that you can call on arrays. And then the source code instrumentation platform will handle user-defined functions as the composition of calls to VM-provided functions. And furthermore, we also accounted for control flow taint. So that is based on control flow wherever your program flows, what dictates that control flow will also account for, or will also taint values that based on control flow statements are now assigned new values. In terms of our API, you can mark sources using taint.source, sinks taint.sync. You can sanitize values using a sanitize function, which is to remove the taint from a tainted value, in a sense that you can consider now a tainted value to be untainted. And we also can assert on taints using assert is tainted or assert is not tainted. In terms of our WebAssembly implementation, we also used a instrumentation framework, which is called WASinstrumentation, as our source code instrumentation platform. So that rewrites a WebAssembly program into an instrumented WebAssembly program with the taint analysis. And we forked a shadow runtime framework, which we call WAShadow. And WAShadow itself precisely follows the WebAssembly semantics to trace values, shadow values of a WebAssembly runtime. So the analysis sort of mimics the runtime semantics. And we changed the tracking domain of WAShadow from WebAssembly values to now taint values. So think of it in the implementation that, for example, any entry that previously in the shadow runtime you were pushing on a stack, if it were a value, a WebAssembly value, now we change that into being a shadow value with a taint status. Now, in more detail, so the shadow values, they track taint at a byte level. So a byte level can then be marked tainted or untainted. And so for 32-bit sized values, that means 4 taints. For 64-bit values, that means keeping track of 8 taints. And then the shadow stack and the shadow global store also continue to compute the taint of the values flowing through the program. And also for the shadow memory, it could be that you are storing tainted and untainted values into memory, which we then keep track of. So for example, in those 2 earlier instructions, the first is tainted, the second i32-bit value is untainted. And if you would then read from linear memory at a slight offset, we keep track of how that taint flows then also through linear memory. A little advertisement, I will be explaining more how Shadow works, what Shadow works in terms of its implementation and use cases during the WebAssembly workshop on Thursday. So feel free to join if you're interested. So next on is the orchestration between the 2 individual Shadow analyses or taint analyses, and the interoperation between JavaScript and WebAssembly programs. And so we focus on 3 boundaries in which JavaScript and WebAssembly programs interoperate: function calls, linear memory, and shared globals. And for our implementation, we ensure that the JavaScript analysis side manages taint communication across the interoperability boundaries, and that the WebAssembly side only exposes the taint communication or only provides its API to read from the taint. And so this is essential, or this architecture is because we consider JavaScript always to be the entry point of a taint analysis. So JavaScript can call into WebAssembly to retrieve a result. JavaScript can call into WebAssembly, which calls back into JavaScript, but JavaScript was the entry point. But we do not consider an architecture where WebAssembly is the entry point of a program to start an invocation, and that is why the WebAssembly end only needs to expose to communicate taint, but that the taint management is performed at the JavaScript side. So let's say that we have a function call in JavaScript. It calls into WebAssembly. On the WebAssembly end, it performs the function execution and eventually it returns the result. Well, the orchestrator, before that function call takes place, shares the taint of the arguments. Then, during the execution at the WebAssembly side, taint is propagated, and eventually the result, the taint of the result is also stored on the WebAssembly side. Then, when the function call returns, before the callee of that JavaScript function gets its result, the taint is retrieved at the WebAssembly side and also passed on when the JavaScript function then eventually returns. There are more details on the semantics of how the orchestration works, which you can find in the paper. Now, in terms of evaluation, we posed 4 research questions, which is, what's the runtime performance overhead for JavaScript's taint analysis? What's the runtime performance overhead for WebAssembly's taint analysis? What's the runtime performance overhead for JASMaint when we combine the 2? And what's the taint tracking precision improvement for JASMaint? So in terms of evaluation, we departed from a multi-language taint analysis that has been developed, benchmark suite, Truffle Taint, that covers 10 programs, and we adapted that input program suite to also conform with control flow based taint assertions, as that earlier work did not support it yet. And so to answer the first 3 research questions, we measured the performance overhead, and we measured the slowdown with respect to the baseline performance, so an uninstrumented program, for 3 key factors. So first of all, for the forward analysis, which we denote as an empty analysis. So you instrument the program, but do not account for any analysis semantics. Then for the shadow analysis, so this is a heavyweight analysis in which you in which you keep track of all values, but do not yet keep track of all taint. And lastly, the shadow analysis with keeping track of the taint of all the values and also accounting for the taint propagation rules. So we did that for 10 programs, and you can see the results here. Note lower is better, and the information is on a logarithmic scale. So first of all, sort of a sanity check. Increasing complexity of the logic, you can see that always there's this upward trend. The more costly the analysis becomes, the more cost you start to pay at runtime. So this checks out. Then we also summarize the entire result of the execution slowdown of a JavaScript-only analysis is 1.72 to 12,000 times. For WebAssembly, it's 250 times to 1,200 times. And for the JASMaint, the runtime overhead is 11.93 to 2,500 times. So this is really costly. It does incur a costly overhead. However, this is within the expected range for portable source code instrumentation. Then we also wanted to evaluate the precision, and so the methodology is to reuse that same benchmark suite. And so what we then do is we trace the execution of an entire program. So at any program statement, we record all the values. And what we wanted to compare JASMaint with is a dynamic taint analysis that could not keep track of taint at the WebAssembly side. So we called that the state-of-the-art taint analysis before we developed JASMaint. And its interoperation semantics is essentially, as long as the JavaScript side provides untainted values to WebAssembly, any value that is returned is also considered untainted. As soon as a tainted value flows into WebAssembly, since that WebAssembly module is stateful, we should consider any value that then is returned to be tainted. Then we compared this entire trace also with JASMaint's implementation, and what you can see is that on the top you have a correct implementation where the true situation, either tainted or untainted, is that both JASMaint and the SOTA implementation return the same result. However, it could be that the SOTA and JASMaint mismatch, and we consider JASMaint as the ground truth, since it can now accurately track the taint also on the WebAssembly side. So we consider those situations to report a false taint information, either that it should have been tainted, or that it falsely is marked as tainted, or falsely is marked as untainted. And so then to measure the precision improvement, what we do is we essentially see, okay, how much can JASMaint reduce the total information to just the true information that only JASMaint will provide. So what's there? The fraction, which is a similarity score, and based on our evaluation, the similarity score varies in between the different programs. So we could reduce the overtaint down to 44% in the best case for Vancouver Redux. However, depending on the semantics of the program, there is less and perhaps less gain in that reduction. So this is, again, the overview. We provide JASMaint, a portable multi-language taint analysis for WebAssembly and JavaScript interoperating programs. And then we discussed, or we evaluated the runtime overhead for each individual component, and also measured how much the precision improves with JASMaint. Thank you.
Thank you very much. Okay, so it's time for questions.
Hello. You said that you've looked at interoperation via memory, globals, and function calls, right? Do you know, like, why did you not look at table mutation?
So the instrumentation framework that we use is instrumentation, and it currently does not support tables. So there are plans to add that to instrumentation, then also add it to the Taint analysis, and then we have a more program whole overview. But we did note that for our implementation, table manipulation was not used. So that additional semantics that we could keep track of does not influence these results.
Oh, I more meant not table mutation in WebAssembly, but table mutation via JavaScript.
We do. So at the JavaScript side, every semantics that JavaScript used as part of these benchmark suites, we also accounted for the Taint propagation there. So all primitive data structures, including VM provided such as arrays, are also being kept track of.
Thank you. Why does the slowdown for JavaScript span 5 orders of magnitude, and for WebAssembly it's less than 1 order of magnitude?
So this corresponds with the overhead expected from the instrumentation frameworks. So using Aäron, or in the paper that describes Aäron and presents Aäron, also the execution overhead, the slowdown is within that same range for different dynamic analysis. And for the instrumentation paper, indeed, also the slowdown for different dynamic analysis is reduced. So it sort of corresponds with the instrumentation frameworks. But it aligns with our expectations, but exactly why it is so slow depends probably on the optimization opportunities to optimize the way that the tactics used to instrument these programs. So on the Aäron side, certain metaprogramming techniques are used to inject the analysis in JavaScript. These could be harder to optimize for the execution engine, perhaps in comparison to the way that instrumentation does it, which is inlining analysis instructions in the target program. So that could be the reason why the overhead on the JavaScript side is so much larger.